Okay, this video is explicitly for Cade, and I guess also with Kivern and Howard on the antenna team. But we're gonna focus on modeling Cade's monopole antenna in the context of how it worked with the radio that we built. So I'm starting with an empty session. I'm gonna go to desktop. Cade, we made this mistake before, where we started with a Maxwell design. So make sure you start by adding. Oh, sorry, I have to make a new project first. So now I have a project, and now they're unshattered. I get to add a design, and I'm going to choose an HFSS design. So let's do that first. My project 2. Save as you go. I'll try to do that as I build this up, but for now I'll just leave it as is. First thing is HFSS design 1 is showing a terminal network. I want you to go to the HFSS menu and change that solution type to HFSS with hybrid and arrays. And I'm going to say OK. And I'm going to save this. It's going to ask me to give it a new name. I'm going to call it, I'll just call it Monopole. Cade's Monopole. How about that? And I'm also going to change the units. Let's put it in units of meters. Okay. And I'm going to do this before I do the import. So I'm going to go to meter, and so now I've got no geometry here yet. So I'm going to save it one more time, and as I go to import that object that you sent me, it should come in meters. So I'm going to go to Modeler. I'm going to go to Import, and I'm going to go find my download directory, which is where it should be. And I think this guy should be this guy. Yeah, on the 3rd of May, just a few days ago, you sent me the modified monopole antenna with the large port. And this is a step file. I think that's good. So I'm just going to say OK, and let's see what comes in. So if I look at the yardstick down here, my ruler, it looks like it's about right. I think if I remember the size of that thing in class, it seems 3 meters seems like a reasonable number. Let's get the exact value though. I'm going to measure an edge. I think you got a few edges here to choose from. So when I zoom in, I can see some edges here. Let me right click in this space and choose the measure mode of edge. And it sees this thing called body edge, and that should be good enough. What's it say on the left-hand side? On the left-hand side, it says the length is 2.465 meters, if you can read that in the measured data panel. So that's what I'm reading off right over here in length. So I'm just going to write that down, I'm just going to round up and say 2.5 meters. And this is important. You'll see why. 2.5 meters equals the length. So I'm just writing this down so I don't forget. And you should maybe do the same. All right. So, okay, let's start with material selection. But before we do that, we're going to merge these objects. If you remember, Cade, we did that in class. So right now, I've got apparently 4 bodies. I can click through them and see where they are. And we only want the ones that are going to represent metal. Right now, instead of modeling the plastic, we're just going to ignore it. So body 1, I believe, is the PVC that you used. So remember, in the properties panel here, it shows up as a model object. If I untoggle it, it now shows up as non-model. That just means that it's not going to be represented in the simulation. So we still get to keep it here in case we change our mind and want to add it later, or we get to see it visually. But we're going to cut a corner and decide that it's probably not going to make much of an impact on the radiation because it's a plastic object, and we're only concerned about the metallic resonator, part of the resonating structure right now. Okay, so with not assigned, what I want to do before I assign these all materials, let's go ahead and unify them. In Fusion 360, it looks like it came across as 3 separate objects. If I control select them, I've got all components, and I'm going to hit this unite. And now you can see I've got body 2 now. is all lumped together, and I'm going to assign a property to that. If I right click body, I'm going to choose assign material. My material window is going to come up, and I'm just going to type PEC and return or enter. It's going to complain about a definition already being there. That's okay. Look, just at the end of all this, make sure that body 2 shows up in peak, and that's good. Okay, so now you may have noticed I went ahead and changed the grid. Sorry, I should say the drawing plane. So by default, you are probably still looking at this. What I want to do is draw something in this. I want to create my port. So if you remember, part of the workflow was create our structure first and assign materials. We've done that. That's the very first step. That's worth talking about in your presentation slides. Now we're going to move on to excitations and boundaries. We're going to set up a port, and we'll set up a ground plane. So this is the excitation and boundaries portion. What I want to do is basically replicate the face of this cube that you put in here and slide it down, and I'll make that the port that makes contact with the ground plane. Those are the things that I want to accomplish. So to do that, I wanted to go to the XZ drawing plane. So now I'm in the proper plane, and I'm going to use this draw rectangle function, and I'm simply going to zoom in on the cube, and I'm going to wait until it appears to find the vertex. I'm going to click the first point. If you look in the bottom left corner, it says enter the opposite corner of the triangle. That's exactly what I'm trying to do, and I'm going to wait till it snaps to that, and it looks like I get it. I get a new object called sheets unassigned rectangle 1. So now that's great. I've got the sheet. I can highlight that rectangle 1, and what I want to do now is slide it down. I want the top of this sheet to be completely aligned with the bottom of the brick that you created. So I have it highlighted. I'm going to use the move function. It's asking me to input the reference point of the move vector. That's the base of my vector. And I'm going to hold the Z button down for me to keep me in the plane. You don't really have to. It's going to snap to that vertex again, so that makes it really convenient for us. That's why I'm doing it this way. And I'm just going to go ahead and hit the second point. So you can see the move command showed up. If you need to adjust it, you could also type the values directly in here if needed. So that's a good start. Great, I've got a port before I assign it. I shouldn't say I have the port yet. I have the object that I want to create the port on. So that's a really good start. What I want to do now is make a ground plane. So I'm going to zoom out. I want the ground plane to actually be aligned with the XY plane here. Okay, my origin is slightly above. What I'm going to do is I'm going to change my plane to XY, so that's good. Anything I draw right now, though, is going to be up at this level here. So what I'm going to do, there's a couple ways to do this. I'm going to create a new coordinate system. Okay, so if you look in here, I only have this guy, the working coordinate system. All I have to do to make a new coordinate system is go up here to this button that says offset origin, and when I do, it's just waiting for me to click. I'm going to click right in the middle of my port. And there we go. I've got a brand new coordinate system, and it shows up here as relative CS1. The W tells me that it's the working coordinate system. Anything that I build from this point on, as long as that's selected with the W there, is going to be referencing this coordinate system. So that's perfect. It makes it really easy for us to make the ground plane. So what I'm going to do is get a normal view where Z is pointed out at the screen, and I'm just going to eyeball some rectangle. I'm going to zoom out. It doesn't have to be big. Just a couple of, honestly, just a few centimeters would be fine. I'll go ahead and make it maybe 10 or 20 centimeters here. So make another rectangle, and I'm going to just click there and click here. And now I have another object that I can make it a ground plane. So yours doesn't, it might not look exactly like this, but as long as I have contact with this object, the sheet, to the brick that you created, the block object for the antenna, and then the ground plane. And that's really all we need. So now I have this. I have the objects defined for the port and for the ground plane. So I'm going to go ahead and put excitations on next and boundaries next. So the first thing I want to do to make an effective terminal port is what we're going to call it, is to have another metal object for it. It wants to see metal objects on both sides. I have a sheet object here, which is, I can't assign a material to a sheet. It's not possible. Instead, I'm going to approximate it with a boundary condition. I selected the sheet, I did a right click on it, and I went to assign the boundary, and now I'm going to choose perfect E. And when I do that, I have two monitors, so if this little form popped up on my second monitor, I'm going to leave it that name. I'm also going to call it an infinite ground plane because it's going to help us. It's just going to help get a faster solution. I'll just leave it at that right now. So toggle on infinite ground plane. Say OK, and I can open up my project tree and just verify that. Excuse me. The thing that we call perfect E is indeed right there. So it acts as metal. So now the port should see, in quotes, metal on both sides. So I'm going to select that port, or the object, the sheet, and now I'm going to right click it, and I'm going to choose assign excitations. And we're going to give it a port. There's all these different port types. We're going to go with what's called a terminal lumped port. So I'm going to choose that. You can change the name if you want. I'm going to go ahead and say use port object name. I think that means it's going to use this port name. I could be wrong about that. It really doesn't matter. You'll see in a second. And now I want to choose the reference for the terminal. So I'm going to choose the ground plane reference. So if you did that properly, you should see just the large ground plane being hashed out there to indicate that it's been selected. So I'm going to go OK. And look on the left-hand side, and you should see I've got excitations. So it took the name that we gave it, number one. Actually, that's not what it was, but that's correct. So port number one is fine. This is the terminal. These two things make up the excitation. Okay, there's the port, and there's the reference terminal. We don't need to agonize too much about what that is at the moment. So that's good. We have a good design, at least from geometry, materials, excitations, and boundaries standpoint. The next thing we have to do is assign what's called hybrid regions for this, and I'll try to explain that while we're setting up in a second. So to apply the hybrid region, we're going to select everything except the non-model object. I don't think it's going to allow us to put a hybrid on that. We certainly don't need it. I'm going to highlight the body one and hit Control H, and that's going to disappear. So now I've got my boundary applied to my ground plane, I've got my port, and I've got the radiating structure here. So that's all my metal. So these three things are perfect for the assignment. If I do a box select coming from the bottom right to the top left, it basically means that anything that touches contact within that box is going to be selected. It's different than doing a right top left to the bottom right select. That select means everything has to completely be enclosed within the box. So that's why I did it this way. So I've got everything right there. I can see body 2 is highlighted, rectangle 1, that's where my port is assigned. Rectangle 2, I believe, is that's my ground plane. So all I have to do now, as you may have already guessed, is I right click and I choose assign hybrid, and I'm going to go with IE region. We talked briefly about integral equations. If this was appropriate, I could possibly choose SBR plus region like we did with the reflectors, but in this case we're doing a lower frequency solution, as you're about to see. So this is the right one to select. And when I do that, I'll see over here on the left hand side of my project tree, I've got this new hybrid one, and you can verify that it's assigned to everything that we think it should be. You'll also notice, of course, that the excitation is assigned. So the excitation has two things assigned to it. I should say that that rectangle, that square has an excitation as well as a hybrid region assigned to it. So now what we have to do now is do the analysis setup. So if I right click this and choose add solution setup, I'm going to choose advanced, and I have to make a decision at the frequency in which I'm going to solve. And it defaults into a single frequency solution at 5 gigahertz for no real good reason necessarily. So we want to make sure that we solve at a frequency where this antenna is expected to operate. So if you can do the math, I'm going to go ahead and roll this out with you. I'm going to fire up a whiteboard, and if I can remember how to get the whiteboard, oh, it's right here. So let me get my tablet, and we'll just do a new whiteboard. So if I remember, I wrote it down here. We have a length for this monopole. The length, I'm just going to put, I'll just do a, oh, that's big. Let's undo that. And we'll change the size to something a little bit smaller. So maybe that's a little bit better. So I'll go with length of the monopole. I'll just say mono equals, we measured 2.5 meters, if you remember. So 2.5 meters. Now, we talked about this being a quarter wave monopole. So that means that this monopole is 1/4 of the wavelength of the frequency in which it's going to operate. So, if you remember, the connection between the wavelength of an electromagnetic wave and the frequency is that multiply them both together and they equal the propagation speed. In this case, in a vacuum, we're just going to say air is like a vacuum, is going to be the speed of light. So this is 3 times 10 to the 8 meters per second in SI units. And this frequency is going to be where we expect this to resonate. Can you remember what the stations were, what the frequencies were of the radio stations that we were picking up with Cade's monopole? We plugged it in. We had other antennas as well. But with that monopole antenna, we were picking up a frequency of somewhere around 1,000 kilohertz, if you remember. I believe Howard ran out to the car to see what frequencies were, and I think there was at least one that was maybe at 600 kilohertz, and one was up even higher than that. We were picking up a couple of different stations there. So let's just say roughly 100 kilohertz, or I should say 1,000 kilohertz. So that's the same. That's also the same as 1 megahertz. So what this is saying, my handwriting is a little bit sloppy here. So this is saying basically the same as 2.5. I'm going to drop the units because we're keeping track of them for the most part. 2.5 is equal to a quarter wavelength, so lambda over 4, which is going to be equal to, if I look at this relationship, lambda is also equal to C over F. So I can say 2.5 is equal to C over F, and actually, sorry, I forgot the 4, so this would be equivalent, right? So lambda over 4 equals C over F times 1 over 4. So this is the equivalent. So let's just bring the 2.5 over on this side. So that makes more sense. So all we did was some basic algebra here based on the dimensions of the antenna that we have. Cade, I believe, chose the antenna because we had a PVC pipe that happened to be this long. We went ahead and put the copper tape on it, and we found out that it was picking up a frequency of about 1 megahertz. So let's solve for the frequency now. So if I just rearrange this, I can bring F to the top, and I can say F equals 3 times 10 to the 8. and then I'm going to bring 2.5 down to the bottom, and I'm going to multiply that by 4. I believe we have everything covered there, right? So F equals C divided by 2.5 to the 4. So let's just, I'm going to pause and just get the calculator for this, and I'll see what we get for the frequency. Of course, I didn't necessarily need a calculator for this one, as simple as it was. Didn't realize that in the denominator we have 2.4, if I can find my pen here. Did I lose my pen? Okay, so in the denominator I have 2.4 times 4, which we know is going to be 10. So 3 times 10 to the 8 divided by 10 is, I'll basically remove, that's 10 to the 1 in the denominator. I'll remove an exponent. So that'll be the same as 30 times 10 to the 6. This 8 goes to 7. And then if I bring it out one more, it'll be the same as 30 times 10 to the 6. So you can verify that. And I'm going to say hertz. So that is also the same as 30 megahertz. Okay. Now, not the same as the frequencies that we were picking up. Okay, but that's okay. We're going to design. We've already built the antenna structure. And now we're going to choose this as the simulation frequency, and then we'll have a quick discussion about how to make this thing work with lower frequencies. So we have just solved for our design frequency here, 30 megahertz. So I'm going to go into Setup or Analysis. I'm going to right-click the Analysis node and choose Add Solution Setup. We're going to go with Advanced, and just follow along as I fill these out. We're going to say 30 megahertz. It's our solution frequency. Make sure if you type it in here that it takes over here. I'm going to go to 15. And when I say OK, it should bring up another window, which is the sweep. We're going to allow the sweep, but I want to make an adjustment here. Let's bring this down a little bit. Actually, 45 is probably fine. But we're going to bring this down to, let's say, 0.01. So would that be, if 1 megahertz is 1,000 kilohertz, this would be 10 kilohertz. So I'm doing that for a reason. If you remember, our intended, the frequencies that we were getting were in that 1,000 kilohertz realm. So I want to solve a little bit lower than where we were receiving the frequencies, and I want to solve up to where this antenna is designed to receive. So two different things. I hope that it makes sense in a second. Let's do a quick preview of that. I can see all the number of points here. So yeah, 10 kilohertz. Here's getting into the AM stations here. This antenna, according to the physics rules that we're using, is not designed to work at these frequencies, but we know we were picking up something, and then we're going to get all these other frequencies bringing us up into the higher realm where we know that 30 megahertz is up here. So we should see performance of this antenna in areas where it's really not designed to work, and it is designed to work. So I'm going to say, okay, the last thing I want to do is create what's called the far field setup. So I'm going to right-click the radiation node, insert far field setup, infinite sphere. We're just going to keep the defaults here, that's fine. And let's change the coordinate system to the one that we're referenced to now. So I went into the coordinate system tab and chose use local coordinate system. And the only one we have to choose from should be CS1. Yours might have a different name. So we'll go with that. And then now I'm going to save, and I will validate, and I'm going to just analyze all. I don't think this is going to take very long. I'm going to pause. Make sure you see your adaptive passes in here. You should get a converged solution after, I don't know, maybe half a dozen adaptive passes. And then it's going to go into the frequency sweep, which it should solve actually pretty quickly as well. So we'll talk about the results when we get back. So I have a solution. If I expand this window out, I should see normal completion. My interpolating frequency completed and converged. My adaptive passes converged a while back, so we should be good. This only took a few minutes for me. I think it's going to be pretty quick on the server. Now I'm ready to look at results. The first thing I want to look at is Instead of looking at a gain pattern, I'm going to look at what we call scattering parameters. So go to results, go to terminal solution data report, and then go to 2D. And when I bring this up, this all looks good. We had a sweep, domain is sweep, terminal S parameters, that's what we want. This is the only value we have to choose. I'll explain that in a second. And we're going to look at decibel scale. So that's all good. I'm going to go to new report, and let's see what we get. So I don't know how much we talked about this in class, but look at this curve. It's in dB scale, okay? It's in decibels. So it's not a linear scale. It's linear on the horizontal axis in frequency, but not in the magnitude. This terminal S parameter is what we refer to as a return loss. And think of the idea of gain. We talked about a black box where I can put 1 watt of energy into it. And on the other side, if I measure 10 watts of energy, then I know that it had a gain of 10. Conversely, if I put 1 watt and I end up with a milliwatt, then it had like an inverse gain. So it was almost a loss. So something happened with the signal that went into the box that for whatever reason wasn't allowed to get out to the other side. Return loss is a way for us to measure if energy is fed into a system through a port, an antenna through a port, how much of that energy is going to make it to the antenna so it actually radiates. We didn't spend a lot of time talking about this idea, but in electromagnetics, signals can get set up on a transmission line like a cable, like a voltage generator, and they can get reflected back. So the smaller this number is in decibel scale means the less energy is getting reflected back, means the intended energy is making it to the antenna. So, excuse me, when I look at this plot for our antenna, this is my return loss for the port, and I can see right here at 29 megahertz, very close to our design frequency of 30 megahertz, there's very little energy making reflected from the port. So we can assume that it works very well at these frequencies. Once you look at something past negative 10 dB and your return loss is below negative 10 dB for the frequencies that you want to operate at, then it's in really good shape. So this tells us now, if I were to go and generate, I'll come back to this plot in a second. What I want to do now is look at the gain of this antenna. I'm going to right-click the infinite sphere, go to compute antenna parameters like we've done with the reflector. I'll expand these out so we can see our solution frequency. If you remember, it's showing here as 0.03 gigahertz. That's 1, 2, 3. That's 30 megahertz. The same thing if you slide the decimal place. So that's good. And we want to look at, let's just say, peak realized gain. So that's 3 in linear. So if I did 10 log of 3, if I did 3 and I did log, that's 10 base log times 10, that's the definition of decibel, I'm getting a gain for this antenna of 4.8 roughly. So that's my gain in dBi for this antenna. Incredibly low compared to our reflector antennas, right? The numbers that we were looking for the NASA system were way above 30, 40 dB, like looking at 60 and 70 dB. So dBi in this case. So 4.7 dBi at the frequency of operation. It doesn't mean it's bad. It just means that it's a low gain antenna. It also means that it's most likely an omnidirectional antenna. I'll show you that in a second. So peak, if I look at the efficiency, that's actually good efficiency. I can see it's 93% efficient. So that's actually pretty good at our frequency. I'm going to close this out. Excuse me. I'm now going to go to results again. And this time, I'm going to generate a far field report. And this is going to be a 3D polar. And when I choose that, there's our infinite sphere. So we set that up before. It's referencing our local coordinate system. So it points out to infinity that we're going to basically present this gain pattern on top of. And we talked about what a gain pattern is. We've got gain, gain total, and I'm going to choose dB scale here. So when that's done, I'm going to hit new report, and this is what a gain pattern looks like for our monopole antenna on an infinite ground plane, which is something we never had. but it's a nice approximation for what it could be. You can see there's our gain here of 5.17. It's a little different than I guess what we calculated, or yeah, it's slightly different, but it's in the ballpark. So it calculates a maximum gain of that number. You can see it down here. If I zoom in, the maximum gain is being shown down here, pretty much uniform in what looks like the XY plane. So as I sweep around at any location in the XY plane on Earth, I can see about the same amount of power for any given distance. I won't see that much power if I'm flying right above the antenna, right? So I can see that little null, the apple core pattern. So it gets really low, as you can see from the color scales. It goes from positive values to negative values. So that's our gain. So far, everything is looking good, except we haven't answered the question of why this thing is actually working. It's working at 30 megahertz, which is what we designed for, yet our frequency, I'm going to right-click in this plot, the terminal plot, and I'm going to choose X marker, I believe. Let's go with X marker. I can slide this out and pick off the value at 1 megahertz, which is the same as 100 kilohertz. 0 dB. So it's not supposed to operate at that frequency, as indicated by this. Yet when we connected this to our radio in the classroom, we know that we were picking up stations that were about 1 megahertz, 1,000 kilohertz. We know that we were picking up those stations, yet according to this, it's not supposed to work. So one thing we never talked about was this very important number right here. When I go up to excitations again, I'm going to double click. I believe it's this one. Let's double click on the terminal. So if it came up on a separate window here. So if I double click on this, underneath my excitation, I've got this rectangle underscore T1. That's my terminal. I've got a number here that I can put in for something called a renormalizing impedance. You've heard of ohms as resistance. Notice here it's defining impedance as resistance plus the imaginary, I for imaginary, times something called the reactance. We didn't have time to get into that detail in the class, but what I'm going to show you right now is how to determine a number that's going to make this antenna work better when it's connected into our actual radio circuit. So some of those components on the radio, the inductor and the capacitor in particular, impact this renormalizing impedance number, and we're going to use the number for the capacitance. And we're going to find out what that number is. I'm going to cancel this for now. We're going to come back here. We know that there's a lot going on, so we appreciate you hanging on all this time. But we're about done here. I'm going to go to results. I'm going to go to terminal solution data report. I'm going to do this one more time. Instead of doing S parameters, I'm going to choose something called terminal Z parameters. And I'm going to plot the real component, and I'm going to hold control and plot the imaginary component with it. So looks a lot like S parameters, but instead it's called the Z parameters. And I'm going to plot them for the entire sweep that we ran. And let's say new report. And now I get something that looks very different. So notice how these values for the real and the imaginary are pretty much lined up and matched for frequencies that are higher frequencies. It's when we get down to the low area where our antenna we were hoping to operate at 1 megahertz where we see something different taking place. I'm going to try to zoom in at 1 megahertz. Let's see, I'm just going to use my pan button. And I'm going to see if I can get as close as I can down here. And let's see if I can just pick off this number. I'm going to put another marker, and I'm going to add a X marker. And you know, I actually should be able to just type this number in. So right here, with the marker, I'm going to put 1. It brings me right to 1 megahertz. What I see here is this green, the imaginary number. The fact that I've got my real component here, which is very close to 0, but I've got this very large negative number for the imaginary component. So I'm just going to approximate that as about negative 7,000. I know it's actually close, but just easier to remember. So I'm going to say negative 7,000. So that's the imaginary component of my impedance, and this is basically showing me what we call a capacitive reactance. It's giving me a value of capacitance that this system sees. So think again, this is our antenna connected to our radio. So if there's some capacitance and inductance in that radio, it's going to be able to pick it up at this frequency. And I'm choosing this number because this is what I'm seeing from the plot. Negative 7,000. I want you to just now go to the rectangle, and I'm going to renormalize this by, I think the convention is, it's negative 1 I, and I'm going to say times this 7,000. So that should be the syntax that is basically plugging in that green number there at 1 megahertz, and I'm going to say OK. And when I do that, I have just renormalized based on the impedance that it sees in the actual system. And when I come back here, what you can see is that all of a sudden my radio was not working nearly as well as it was working up, before at 29 megahertz. If you look at the return loss, look at how it has dramatically changed. And now at 1 megahertz, all of a sudden, it's performing very well because the impedance now is very, very different. Because I put in that number of negative 7,000, I can see that I'm hardly getting any reflections at that point. I want you to keep in mind this concept of the antenna being connected to the radio that has the capacitor that we've been designing in class, along with the inductor. So this is the effect of tuning the radio. So by choosing the appropriate capacitance value, it's going to change the way that antenna is able to interact with the environment and bring a signal inside the receiver. So this is pretty significant and a pretty important part about how our radio is working. I want to end with one last thing to attempt to tie all this together. This is a snapshot from a very quick search that I did using Bing Copilot also, which was pretty nice. I basically searched on the capacitive reactance, and it gives me this formula. And if you can look at some of these terms here, this is basically, let's just work out the math here. If we say 1 over 2 pi times the frequency of the AC signal in hertz. That's the signal that we want to receive. This is the AM radio station of about 1 megahertz, or maybe a little bit lower. So we're just going to put that number in. We're just going to say 1 megahertz. And then the last value, let me extend this out. This C is directly related to the number that we measured. So I'm going to put in a value of 7,000. We're going to say that the negative sign is implied here, so in the impedance at least. So I'm going to say 7,000. So if you work out this math, I'm going to just plug this into a calculator real quick. I'm going to pause this while I run this calculation out so you don't have to wait through this. So if you punch all this into a calculator, what I ended up with was 22.7 times 10 to the negative 12. And I am just telling you that this reactance, the XC here, is capacitive, so it's going to be a value in farads, which is the same as saying 22. Whoops, that's a little sloppy, but I think you can see that's a 22. It's supposed to be picofarads. So if you go back to some earlier work that we had done right at the beginning of the semester when we were building the radio, my question is this a number that we were able to achieve with the radio design that we were working on? And if I come over here, you might remember the capacitor that we've been simulating in class was designed to fit within this footprint and achieve these values. And I can see, depending on how we wire this guy up, we're going to get values anywhere from 0 to 532 picofarads. So remember what sits on top of this. There's a dial. So as we turn that dial, we are changing the value of the capacitance from somewhere between 0 and 532, of which this number, 22.7, is in there. It's on the lower end, but it's there. So if we are tuning to 1 megahertz, then this value, neglecting the effects of the inductor, which we should probably have in there, but this is a dominated by capacitance event, that value is going to give us a tuned station to that particular signal. So you could imagine if we dial it to the right or to the left a little bit more, this value will change. We could measure the impedance again, just like we did, and we would find that it's going to pick up a different frequency that we were interested in. So we could go a little bit lower than 1,000 kilohertz, or maybe a little bit higher, just like the full gambit of the AM station spectrum. So in a very clear way, we have tied the performance of this antenna for the radio that we actually verified in class to a value of capacitance that we're able to get from the capacitor that we are attempting to simulate in class as well. So thought you might think that's pretty neat, and feel free to research reactance and impedance, and kind of go back and watch the video of how we did that whole process, and it might help tie together all of the concepts that we've been working on here.